I'm Melissa.
I'm Jam.
And I'm a chemist.
And I'm not.
And welcome to Chemistry for Your Life.
The podcast helps you understand the chemistry of your everyday life.
Hey, Jam, how you doing?
Dude, I'm good. Drinking some tea. Just trying to keep warm, you know?
Yeah, it's been chilly in Texas lately. Pretty cold for our standards, but I've been loving it.
Yeah, me too. It kind of feels like actually winter, which is funny because it just seems like not that long ago that it was kind of like, man, other parts of the country are experiencing the new seasons and we're not. Why is it still so hot here? And it's just what feels like a few weeks later only. It's very cold for us, for Texas.
Yeah, and the only drawback that I found about the cold is that now we have to be more creative in how to safely hang out with others due to COVID.
Yeah, and with how dark it gets too. It's like fewer hours we have and also less ideal temperature for it. So
yeah, definitely. I've been favoring spaces that are outdoors with an industrial heater.
Nice. I've been hanging in my garage more than I would have expected. It's like less cold than outside, but not necessarily great. I mean, there's no wind, so that's good, but yeah.
Yeah, garages are great. I saw some people in my neighborhood who had some mosquito net over their garage.
Oh, nice.
I was like, so you just open the door and it feels like you're outside, but you don't have to deal with mosquitoes. That's genius.
Yeah. Wait, did they do that recently? Or, because I don't think there's many mosquitoes out right now.
I think it was probably over the summer, but I just drove by that area today, so.
Oh, okay. Gotcha. That's
but a very smart hangout session, you know? Yeah, it's an outdoor space without the irritation of the bugs.
That's huge.
In other news of huge things, we're going to talk about something that Jam has been waiting for a long time.
It's true. I know just what it is, but not anything else.
And that is non-Newtonian fluids.
Yes, dude, I'm so ready for this.
So for those of you who don't know, non-Newtonian fluids we're going to talk about what they are, but an example is the cornstarch and water situation. And I think a lot of people have done that. You mix cornstarch and water up, and if you poke it really hard, it feels like a solid, and if you go slowly, it feels like a liquid.
Very crazy.
Very crazy. So that is what we're going to be talking about today. And it might seem like, oh, this is going to be a really simple science at home kind of explanation, but it is not.
Whoa.
Yes, the chemistry here is very complicated. In fact, it's studied by rheologists, and I had never heard of rheologists before I started looking up these papers. These are scientists who specifically study how materials flow or deform under force or applied pressure.
Wow. Weird.
And they basically have really only in the last 10 years started to figure out what's going on with these non-Newtonian fluids. So I'm going to do my best to communicate to you what I know, but I am just going to give the disclaimer that I may not fully be able to answer your questions, and I think there may be some misunderstanding or maybe some misconception that hasn't been cleared up in the wider science community yet. So there may be things that aren't 100%, but I did my best and I got the best, most reliable sources I could. So I used the American Chemical Society, I used Chemistry and Engineering News, which is a magazine associated with the American Chemical Society, and I looked up other papers for people from rheologists who had studied this.
Nice. Dude, awesome. I've been very interested in this ever since I saw, I think probably the highest profile version of this that a lot of us lay people saw was on Mythbusters, where they were the first I knew of that tried a large scale run across cornstarch and water thing, see if you can move fast enough to run across it and it feel like you're kind of running across a solid thing.
The only thing I've seen with this is our mutual friend, Daniel, once sat in the back of another of our mutual friend, Grant's truck that was lined with tarp and filled with cornstarch and water because his dream was to take a bath in cornstarch and water.
Wow, I cannot imagine how much of that they had to buy. I guess really just the cornstarch, but man, it seems like it'd be hard to get a lot of it for us regular folk. I mean, you'd have no need to get that much of it for any other reason.
I know.
But ever since that, I've been obsessed with it. I remember like doing little just experiments with it at home for fun and stuff, but have never understood what could be going on there.
Yeah, it's pretty amazing. I'll say that. I also want to say that the reason we're doing it and the reason that Jam knows about it is it was a request by Mr. Hollis. He is a chemistry teacher in Illinois who invited us to come speak to his class. And so we've done that a few times now, and it has been really, really fun.
Virtually. We've not taken any trips to Illinois, unfortunately, but...
That's correct.
Yeah, but that's been really cool.
And he requested that I talk to his class about this, so Jam had to bail out because he hadn't learned about it yet.
Yeah, I think Mr. Hollis thought we already had, which is like such a fascinating topic. And so I was like, I definitely don't want to learn about this before I learn about it on the podcast. So we were both okay with me skipping out on it just to wait a few more days before learning it for real.
So that's how we came to be where we are today. So a non-Newtonian fluid, before we talk about that, we have to talk about what a Newtonian fluid is.
Okay.
Okay, so I want you to picture in your mind either honey or maple syrup.
Okay.
And you know how they flow kind of slowly.
Mm-hmm.
The rate at which a material flows, or maybe the more proper term is resists flow, is called its viscosity.
Mm-hmm. Mm-hmm.
So that's if it's more viscous, it's thicker. If it's less viscous, it's thinner.
Okay.
And when I say thick and thin, I mean flows more quickly, flows more easily.
Okay, got it.
Okay, so if you want honey to be more viscous or less viscous, how do you change it?
You heat it up.
Heat it up, and that gets it more or less viscous.
Less. It becomes
That's right.
thinner and less viscous and flows more quickly.
And I know from experience when I tried to put honey in my cold brew iced coffee one time, that if you want it to be more viscous and basically turn into a solid, you put it in colder temperatures.
Yeah.
So that is a Newtonian fluid, a fluid that will flow more easily if its heat is increased and will flow less easily as it gets cooler.
Okay.
The viscosity of most fluids are not changed if you apply pressure to them.
Okay.
So, for example, if you push on water, it won't suddenly change its viscosity to make it thicker or thinner. Or even if you push on honey, it won't change its viscosity, right?
Right. At least not that I've seen.
Not that you've seen. And same thing with honey or maple syrup.
Mm-hmm.
If you push on those, the pressure and the viscosity have nothing to do with each other.
Right.
So that is a Newtonian fluid.
Okay.
A non-Newtonian fluid is one whose viscosity is impacted by something other than just heat. It is impacted by pressure, force, friction applied to it, something like that. Any kind of applied pressure can impact the viscosity of a non-Newtonian fluid.
Okay, so it kind of seems like there's characteristics that are true of most fluids. And so that ends up kind of being labeled as Newtonian fluids.
Newton discovered the relationship between heat and viscosity, I believe. So I think that's why it's Newtonian.
Got it. So when he discovered fluids, he thought there were only these kind that could exist.
Only these kind.
But there ended up being some other kinds that don't behave like he expected.
That's right.
Okay.
And so these misbehaving fluids are non-Newtonian fluids. And that pressure that you apply to them is sometimes also known as shear. It's like pressure or force or friction, shear. So sometimes applying pressure or force can result in more viscosity. So those are called shear thickening fluids.
Okay.
An example of that is oobleck. You squeeze on it and it feels hard. It resists flow.
Right. And oobleck is the term for cornstarch and water?
Cornstarch and water mixed together, yes. I probably should have said that at the top. The cornstarch and water combo is sometimes called oobleck.
I've seen that word used to describe it on like YouTube and stuff, but I have not really heard if that was a kind of colloquial thing, or I didn't know where that word came about, because I think for a long time it was just called cornstarch and water on like, the Mythbusters episode and stuff.
I think it is colloquial, and I think it came from a Dr. Seuss book, actually.
Oh, interesting.
But I did hear a scientist use it in their talk in a presentation to the chemistry department at UNT. So
I mean, it's nice for it to have a word
yes,
instead of just being the ingredients every time.
Yes, it really is nice to have a name for it. I am very appreciative of that. So those are things that is something that you apply pressure and it gets thicker. Another place where that happens is actually in the fluids around your joints.
Oh.
They actually get a little bit harder to cushion blows.
Interesting.
They can absorb some of that impact. So it's not, I think, so that it's not just like bone on bone.
Mm-hmm. Whoa, that's cool. That makes a lot of sense. I didn't think about there being like potentially some benefits to it in a way that it might occur on purpose like that.
I know. Isn't that amazing?
Yeah, that's crazy.
So then there's another kind that I think you're going to be familiar with, but I think it might be hard to place it.
Okay.
And that's called shear thinning or pressure thinning. So something that you apply pressure to and or force or friction, you can shake it or like rub it between your fingers and it starts to get thinner.
Okay. I think I have an example of this, but it's cheating because I think I heard of this somewhere.
Okay. What do you think?
Okay. I've heard that ketchup is one of those.
How have you heard that?
I don't remember, honestly. I did not come from my brain originally, so I wish I could give credit somewhere. But
sneaky.
In my head, I have it stuck in there because something I watched at some point said that was like the opposite. I mean, it even could have been in a book or something. I don't know. But I remember thinking, oh, I mean, like, remember glass bottles of ketchup? It's so hard to get it out. Mm-hmm. But you can shake it up and it moves around just fine. But then you're just like turning it upside down and it's like the opposite. It's like when it's still, it's thicker. And when it's being moved and jostled, it's thinner. It seems like that anyway.
That's a great example. Can you think of any examples where you aren't cheating? I'm proud of you for knowing things and for improving your knowledge base, though. I'm always proud of you for knowing things, but I thought that was for sure going to be a shocker for you. So
yeah,
kind of disappointed.
Sorry. I didn't even know we were going to go there. I just you started asking about the opposite qualities, and I was like, whoa, there's this folder in my brain that's coming to the forefront. It's like my brain librarian is like, actually, you know what? We've got a folder on this. Here it is. Catch up.
Brain librarian. That's funny. Okay, so can you think of anything else? If not, I can lay some out.
Okay, so appears to get thinner when it's being manipulated some way and force is being put on it.
Yes.
Dang, dude. I don't know.
There's one that comes up in movies a lot.
The
more you move around, the more you sink into it.
Oh, quicksand?
Quicksand is a non-Newtonian fluid.
Oh, classic.
It is a shear thinning non-Newtonian fluid. Also, shaving cream, as you move it around, it will change its texture.
Oh, yeah.
And another one that gets used a lot is shampoo, although I'm not sure I've seen that with shampoo, but I can get behind quicksand, ketchup, and shaving cream.
One thing I've noticed about shampoo is that if you put some in your hand and you push your finger in it quickly, your finger will come back out without any on it. But if you go a little slower, it will stay on your finger.
Interesting. So maybe that is an example of a shear thinning fluid.
Interesting. You know what maybe you could kind of chuckle when you brought up quicksand is that John Mulaney joke. I think it's his.
It is his.
Yeah, where he's like, as a kid, I really thought quicksand was going to come into play much more in my life.
Yes.
And
absolutely. And then at the end he goes, looks like regular sand. But then you're going to start to sink into it.
It's just like so funny because I felt exactly the same way. Like when you see that in movies, just thinking like, oh man, I've got to keep that in my brain somewhere because I got to keep a lookout for that. Who knows when I'm going to be just on my way somewhere, anywhere, and I'm going to stumble into some quicksand. I got to remember not to struggle, not to move too much, and hopefully spot it before I even get into it.
That's exactly what I thought about. That's what I think about anytime I think about quicksand. I listen to John Mulaney's stand-up comedy a lot. Yeah. Okay, so now you have some shear thinning liquids and some shear thickening liquids. Do you want to take a pause? You've kind of been along with me for the ride, but do you want to take a pause and explain that back to me in your own words?
Yes, I would love to. Okay, so there's fluids that abide by some rules that Newton observed and probably at the time thought were kind of the norm for every kind of fluid when he observed
Definitely.
these qualities. And it was that the viscosity of a fluid can be changed by temperature or whatever, but not by other factors like force applied to it, pressure or whatever.
Mm-hmm.
And as we have gone along in time, it's been a few years since Newton was doing his thing. And now we've come across some fluids that definitely are affected by being agitated. Their viscosity changes in different directions based on how they're being manipulated. So whether it's a lot of force being put on it and it becomes much more viscous while the force is being applied to it, which is the shear thickening fluids, or the other way around, where when you apply some sort of force to it, you stir it really quickly, you push on it really quickly or whatever, it becomes thinner, shear thinning fluids, and their viscosity decreases while it is being agitated in some way. Is that correct?
Yes, that sounds exactly right to me.
Okay, perfect.
Now let's talk about the science behind it. There are two things that I've seen so far, so I'm just going to summarize those two things the best I can.
Okay.
One thing that I've read is that they're polymers or solids that have intermolecular forces to act as one wide network of solids suspended in some kind of liquid.
Okay.
And those polymers under different conditions, or the network of solids under different conditions, will act differently. So in shear thinning fluids, they would theoretically have intermolecular forces that cause them to be able to take a certain amount of pressure. Once that pressure or force has overcome what you need to break the intermolecular forces, then the polymers could slide easily back and forth between each other. They're no longer one solid network. They've now been broken down into smaller pieces so they can easily move around between one another.
Okay.
So that's one theory on the shear thinning liquids.
Okay.
And in that way, they're not even really liquids, right? They're more solid suspensions, which I think is kind of why they act non-Newtonian, is they're not really liquids, they're fluids, but they're not really liquids in the same way that you would think about it. It's solids dispersed in a liquid medium almost.
Got it. Okay.
So for shear thickening, you're basically going to have the same thing that we talked about on our episode about eggs. So you'll squeeze on whatever it is, apply that force, apply that pressure, and you'll have your polymers quickly unravel and then start to interlock with each other, and they make the solid resisting flow. And then when the force is reduced, they can start to unravel.
Okay. Interesting.
So that's one theory or one type of idea that I got from the American Chemical Society.
Okay.
That makes a lot of sense to me for the shear thinning process, but for the shear thickening, there's something else that made a lot of sense for me as well. And I think this has got to be what's going on with cornstarch.
Okay.
So really, there are super fine particles suspended in water. Super small, very, very, very fine particles of cornstarch suspended in water. And sometimes when you get to particles that small, they start to act a little bit different than larger particles. So now that we have these super small particles suspended in water, they can experience what's known as intergranular or between the grains repulsion. So imagine like if you have two magnets and they both have the negative end and you try to bring them close to each other and they just slide off of each other.
Yeah.
It's like that.
Okay.
So, but on the super small scale, as you're trying to force these super fine particles really close together while you're squeezing it or putting pressure on it, they will start to repulse one another. And then you're experiencing that as a solid because as you push, you're feeling the repulsion that these grains don't want to get any closer than they already are to one another.
Oh, interesting. Okay. Because you're trying to push them closer, then they resist.
Mm-hmm. But if you have small applied stresses, smaller forces, it's not going to be as intense because they have time and space to move away from one another. So you're not feeling the repulsion in the same way.
Right. Interesting.
But I didn't see that applied to shear thinning suspensions. I only saw that applied to shear thickening suspensions.
Mm-hmm.
So those are the two best explanations I got. One is the polymer and the other is the fine particles.
Mm-hmm.
I saw very briefly someone talking about quicksand mentioning that essentially there just wasn't friction between them and that's why it got to be thinner, but I didn't feel satisfied with that explanation, so I would need a little bit more.
Yeah.
So if there are any rheologists out there who know a lot about non-Newtonian fluids, I would love to hear from you to explain what you know. But I will say I found a paper as old as 2011 and as new as 2017 that seemed like there was some disagreement about exactly what was happening. There's one that at MIT, this was the one that talked about the superfine suspension of particles.
Uh-huh.
They were actually able to use computer modeling to predict the behavior of oobleck in different situations, just so they could understand it and then work on applying it to different things.
Interesting.
And actually, Mr. Hollis with his class had them come up with different ideas for what the application could be of cornstarch and water type substances. And they talked about you could use it for impacts for car accidents. In the same way it cushions the blow that you've got going on in your joints if you have a seat that somehow responds to force in an appropriate way to protect your body. Maybe that fluid can be an added safety feature in a car, which I thought was really cool.
Interesting. Yeah, that is cool. Huh. Especially if you mess with the ratio of okay, how cornstarchy is this or whatever, and maybe find the right mix that doesn't make it become too hard or something, but helps it firm up or something like that. That's crazy to think about.
And in fact, I read an article in the American Chemical Society where they talked about a synthesized polymer, I believe, that is a non-Newtonian fluid called D3O.
Mm-hmm.
Just sort of like water, H2O, but it's D with a small 3 and then O.
Uh-huh.
And they are using it in applications in bulletproof vests, in helmets, and knee pads. And they even talked about how it could be really useful in cell phone cases. If you drop your phone and it has this impact absorber that hardens and takes the impact of the force, then it won't shatter your case as much or your screen as much. So really there are all kinds of applications for non-Newtonian fluids in the world. And even one article I read was about an engineer whose job was figuring out how to move sludge in city settings to better places or to get rid of something that's not in the right place for the city or is not looking good or whatever. So there's all kinds of applications for understanding how non-Newtonian fluids flow and for using it in everyday life.
Wow. Dude, the idea of using it in some sort of armor kind of protection thing immediately made me think of mithril from Lord of the Rings. Obviously, that's not a fluid, but just the idea of it's just light, thin, very flexible, little, just thin layer you put on. And then it's can take a ton of force or whatever.
Yeah, then you're protected.
Yeah, that'd be cool to have a thin layer of this something that just has a thin layer of that D3O in it.
They said it's usually best if it's layered with other materials, but that seems like a really good thing to make it lighter but still be able to withstand those impacts.
Yeah, dang, that's crazy, dude.
So that's it.
Wow, dang.
That's how cornstarch and water, that's how ooblecks.
Wow. Yeah, oobleck, is that also, is it noun and verb, both?
I guess if we're making up words, we can do whatever we want. We might have to ask Dr. Seuss.
That's a good point. R.I.P.
So while definitely a highlight of my week was going and talking to Mr. Hollis's class, I was thinking maybe since that's kind of already been talked about, we should share a different thing that made us happy this week.
Okay, fair enough. That sounds good. So mine is, you probably wouldn't know anything about it, but one of my podcast co-hosts with this podcast that I do called Chemistry for Your Life got me a, it wasn't a joke. That's really true. Okay. Got me this insanely cool book that I have wanted for at least 2 years, probably. And when I first ever discovered it, like found out that it existed, it was not available to buy in any reasonable way that I could find in the United States. And it's called The World Atlas of Coffee by James Hoffman, who's like my coffee hero. And
yeah, I've heard Jim talk about him a lot.
Yeah. He's great. Definitely check him out on YouTube. He's amazing. And this book is super cool. And we've talked about him a ton, and I didn't even really see it coming, but Melissa was asking some question about him. I was like, oh, I'm on his website and he's really legit and stuff. And I was like, oh yeah. And she mentioned the book, and I said something like, oh my gosh, dude, yeah, that book seems so cool. I've tried to get it for I put it on my Christmas list for 2 years now or something. And then the next day, when we had a social distanced hangout with Melissa and her dude, she was like, oh, hey, I got you something. And it was the book. And I was like, holy. So it
was so fun.
Very excited. It's hard for me to get super excited about gifts, partly because I'm so picky and have such weird interests and stuff, but this was such a perfect thing. And it was also so easy because it was so obvious that it was something I was going to get a lot of enjoyment out of and was very interested in, and had not bought for myself. That's the problem, is that I would typically maybe have bought this for myself already if I had had the chance to. So I'm very excited. And if you were wondering, it actually was Melissa who got it for me. It wasn't some other Chemistry for Your Life co-host.
To be fair, it was very low-hanging fruit. Also, I saw a year ago in a gift guide, I think it was that exact book, but it was some kind of information about coffee book, and made a mental note to buy that for you at some point. And then it kind of all came together when I was looking at the website. Yeah. Because we're thinking about doing our episodes on coffee. So I went to his website to look for those, and then I saw that he had a book, and it all came together perfectly.
Yeah, I'm super excited. I got kind of sucked into it that night and was flipping through it and stuff, and was just going to look at for a couple things. I ended up spending way more time in that book than I had expected. And Em was like, yay. I was just standing in our bathroom, and Em was like, are you going to come to bed, or could you go read that somewhere else and not have just the light on in there? Or close the door. It was just so funny, but I got really sucked into it. So I'm excited. Thank you.
Well, on the theme of things that I bought for people, I am not wealthy, and I don't often buy this many things. Okay. So just listen, it was, both of them were happy accidents, but I wanted a KitchenAid stand mixer for a very long time. I love baking. But it's a big expense, and you have to be sure you really are going to love the color that you get, because you're going to have it for the rest of your life. And there's never been a color that seemed exactly right, and the time never seemed right, or I'd be short on money or whatever. And then happily, one of my friends sent me a picture of the KitchenAid 100-year collection. And I was instantly in love with it. It's misty blue, which is my favorite. I love that kind of grayish blue color. It had a white stainless steel bowl instead of the typical regular stainless steel color. There was white accents. It was beautiful. And I instantly fell in love, and it was out of stock. But I just knew that I had to have it, so I kept refreshing and refreshing and refreshing. And it came back in stock the next morning, and I purchased it very quickly. It was on sale for $100 off, because it's a limited edition. It's the end of the time I think that they're going to be running it, or maybe not. Maybe they're tricking me, but it was still $100 off its full price. Yeah. And so it was such a good deal, and the timing was right, and I finally am financially stable, and I got myself a KitchenAid stand mixer.
Dude, awesome.
I'm very happy. And there was a more expensive one that came with a ceramic bowl, but I just bought a separate ceramic bowl, and my beautiful white stainless steel bowl and that ceramic bowl together were less expensive than the other one. So I think I made the right call.
Nice.
I love a good deal. So I was very excited about that.
It's also just so awesome when there's something you've wanted for a while is achievable for you, especially if it feels like it used to pay off to wait for it, because this one's more the color that you like, or it's cheaper, or in this case, both. And you were able to get just the best of all worlds, and it was worth the wait. That's such a great feeling.
I mentioned to someone that it felt really impulsive, and they said it's an impulsive purchase, but it's not an impulsive want. You've been waiting for years to get this.
Yeah.
So I'm very, very excited, and it will come in handy for me baking all the baked goods for people once this COVID is over, because I love to bake cakes and treats for people. So I'm very excited.
Absolutely. Yeah. It's been too long that I've been able to have a spontaneously baked thing of Melissa's. Sometimes it's like a leftover, like, hey, I made this for this, but I have some left. Who wants some? And stuff. That used to be a regular thing, and it has been a while since I've been able to experience that. So I'm also glad that you got that mixer.
Yeah, the frequency will increase just as soon as COVID ends.
Dude, that's awesome. Congrats.
Thanks, Jam. Thanks for being excited for me, and I'm glad you really love your book, and thanks to all you listeners who have come and showed up and learned about the craziness of non-Newtonian fluids.
And thank you for teaching us. Thank you for demystifying. It's still very interesting and mystical in a lot of ways, but at least to some degree, demystifying this chemistry mystery that I've wondered about for a long time. And I'm sure that many other people have too. So, and these are the kind of questions that we want to hear from you. Ideas of topics, things that you've wondered about just like this. So please reach out to us on Gmail, Twitter, Instagram, or Facebook at Chem for Your Life. That's Chem, F-O-R, Your Life, to share your wonder and thoughts with us. If you'd like to help us keep our show going and contribute to cover the costs of making it, go to ko-fi.com/chem4yourlife and donate the cost of a cup of coffee. If you're not able to donate, you can still help us by subscribing on your favorite podcast app and rating and writing a review on Apple Podcasts. That also helps us to be able to share chemistry with even more people.
This episode of Chemistry for Your Life was created by Melissa Collini and J.M. Robinson. References for this episode can be found in our show notes or on our website. J.M. Robinson is our producer, and we'd like to give a special thanks to N. Newell and A. Hefner, who reviewed this episode.